So, would you like to introduce yourself?
Yeah, I'm Nicholas Evans. I'm an associate professor of philosophy at the University of Massachusetts Lowell.
And what would make you an expert in topics like gain of function and whatnot?
I wrote the first dissertation on gain of function research and the ethics of gain of function research. So my PhD was on the limits of scientific freedom when national security is at stake. And I started my studies in 2007. And I was finishing my write-up in late 2011 when some studies caused some controversy called gain of function studies. And so the back half of my dissertation is actually about the original gain of function experiments that were revealed in 2011 and came out in 2012.
Awesome, awesome. Now, would you like to explain what exactly gain of function is? Because I know there's some confusion between gain of function and, say, ePPP
Yeah.
research.
So gain of function research arises when a piece of, it's usually virology research, but you could do gain of function with bacteria or fungus or prions or other microbial organisms, let's call them. When you take a pathogen, so a microbe that infects a host and causes disease, and you enhance its virulence, so its ability to kill its host, its transmissibility, so its ability to move from it's called its host range, so the kinds of hosts that it is able to infect. So the classic version of gain of function is to take a very dangerous strain of influenza that only infects birds, and to manipulate it so that it is not only able to infect mammals, but is able to jump between mammals. So right now, for example, there is a large avian influenza outbreak in the United States and Canada, and for the most part, this is only in livestock, in poultry, in cows, maybe in deer, and very occasionally you will have someone get sick, a human gets sick, usually because they're working with the animals and they get the virus. But so far, no one else has been infected by the human that gets avian flu, which is good because the current strain of H5N1 avian influenza kills about 60% of the people who get it. So it's extremely dangerous, but right now it doesn't jump human to human like, say, COVID does. And so in 2012 or 2011, some scientists announced that they had created a strain of H5N1 avian influenza that jumped between ferrets, which is what scientists use instead of humans to study influenza. And so the consequence of this was everyone got very scared about the idea that someone had created a version of this very, very dangerous disease that had the one property that kind of made it less worrying, which is that so far it couldn't jump human to human.
So, as I understand it, the big issue, the dilemma with allowing or not allowing or restricting of some way of gain of function research is the human error factor. Could you talk on that?
So in 2011, when uh, gain of function first happened,
Mhm.
people weren't really worried about human error. What they were worried about was security. They were worried that a rogue state like North Korea would get a hold of this research and they would use it as a roadmap to design their own novel, so new, very dangerous biological weapon. Um, that was what we were worried about in 2011, 2012. But in 2014, people started to change on what they really cared about, which was they started to worry that it wasn't if someone was had bad intentions. It was just if someone dropped the wrong test tube, let's say, right? It's not actually a test tube, but you get the idea, right? That they would infect a ferret with one of these viruses, and then ferrets are notorious for getting out of their cages. If you ever met anyone who owns a ferret, it's the thing that they do best. And researchers lose ferrets all the time. And so the idea was that a ferret would get out with one of these really dangerous viruses in it and maybe bite one of the animal handlers or otherwise escape into the wild, or someone would accidentally stick themselves with a needle that had the virus in it, and that would then generate a infectious disease outbreak of one of these really dangerous experimental diseases. So the conversation shifted from what if someone has bad intentions to what if someone just makes a mistake, and all of a sudden we have one of these dangerous viruses on the loose. And so that's really what the conversation has been about since 2014.
And what would you say, if I may, what would your personal opinion be on allowing or disallowing or restricting gain of function research and ePPP research?
Yeah, so for your audience, ePPP research are enhanced pathogens of pandemic potential. So there are PPPs, there are pathogens of pandemic potential like COVID, and then there would be ePPPs, so taking one of these pandemic viruses and turning it into something worse, right? So something that has the potential to become a pandemic, turn it into something even worse. Um, why would I kind of what do I think the rules of the well, I think that one of the things that we have to understand is that um, this is a really interesting form of science. It's science that is kind of like throwing a dart blind at a dartboard to try and figure out the evolutionary possibilities of viruses. So one of the things that we know about influenza, for example, is that influenza is always mutating, it's always swapping genes with other influenza viruses. That's why you have to get a flu shot every year because it's never the same virus twice, year to year. Um, so the reason that people think you need to do these kinds of studies is that we need to know where the next terrible pandemic is coming from, right? So what is the next COVID going to be? How far away are we from having it happen? Um, and they will point to these studies and say that these are the that we figure out when the next big one's going to happen. The problem that I and others have talked about is that yeah, you might find a way that a virus could change that would be a serious risk to humans, but it's not like you're finding the way because there are so many ways that evolution can go in viruses that could give you similar dangerous results. The idea that there's only one little gap in like, all of evolutionary history where this virus could become dangerous to humans seems unlikely. And so you're creating a virus that's dangerous. It does pose a risk to humans, um, were it to get out. And the benefit that you've gotten is one idea of what might happen. But that doesn't mean that you've actually answered the question of what will happen. So you've created a big risk, but you haven't really created the kind of benefit that you think you have. And so that means that we then kind of run into the situation where we're creating more risks for ourselves without the benefits. And that's why I think that we probably shouldn't do this research very often, right? I think that there's probably the occasional reason to do so, and there's different ways of doing this research, and some of them are better than others. Complicated situation because there's lots of different ways to do science, but in general, I think that the reason why you might restrict these is because the risks outweigh the benefits.
That's a great answer, and I would like a follow-up question to that.
Yep.
What adjustments would you make to this type of research, like regulations, or to make it more precise or efficient, that would sway you towards favoring it a bit more?
Yeah, so let's take the two studies that came out in 2011 uh, that were designed in this kind of way. One was done in Wisconsin. One of them was done in the Netherlands. And the one that happened in the Netherlands, what they did in very simple terms is they took a H5N1 virus and they forced it to become transmissible between ferrets, right? So all they whether or not you could do it. The other study, what they did is really quite interesting because they wanted to see what would happen if two different viruses got together and kind of compared notes, let's say, inside a host, and then got back out, and if there was a possibility of a real risk of a pandemic from that. And the two viruses that they picked, there were some other bits involved, but the two main viruses, one was again H5N1 avian influenza, and the other was the 2009 strain of H1N1, which back in the day we called swine flu, right? So the swine flu pandemic. Now, um, we know that most of the time when flu viruses get going in humans, it's often because two different viruses meet up, they kind of switch parts, and then the new thing is the thing that gets us. And so what they did is they created a library of millions of different combinations of viral proteins, and then they screened them to figure out which ones were most likely to be able to bind to human cells. And they came up with seven like seven different flavors of flu virus that could do this. And then they tested those in animals, and out of those, one of them was able to then jump between ferrets. So they didn't just like brute force this thing. What they did was they showed that out of all of the millions of combinations that they could find, like create of flu virus, only seven to really get into mammals. And then only one of them was really able to take that next dangerous step. So they didn't just show us that it could be done, they gave us an idea about how likely it was that you would get that final result. And so this became, this I think is a very different experiment. And if I had my druthers, I would probably say that the first kind of experiment is the kind of experiment that we don't really have an interest in doing. The second kind of experiment is it's much harder to say that because they didn't just show that it could happen. They kind of showed what would need to happen in order for those viruses to really take shape. Um, so you could imagine experiments that give you the right kind of knowledge and they give you the right kinds of information to make decisions, whereas others just show that something can be done. And maybe that's a good place for regulators to start when they think about whether or not they should fund this research.
So to clarify, you would rather these type of research experiments to be a bit more thorough and finding specific information that will be useful for predicting these type of pathogens instead of just seeing if something could happen.
Yeah, and so one of my first degrees was in physics, so I have a bit of a bias about the way that science gets done. But one of the things that biologists have often noted in their own literature is that there's not a lot of like really deep theory in biology, right? We have Darwin's kind of principles for evolution. We have something called Koch's postulates around what causes viral infections, but it's not like physics where like you've got this beautiful architecture of all of these different laws and rules and theorems. um, and part of the reason that we don't is that scientists follow what they can get away with researching in order to keep their jobs, right? You have to get tenure, you have to stay working for the company that you work at, whatever it is. And so we fund these kind of theory-free experiments in biology without necessarily funding the more foundational biology or enough of it to actually make real progress in biology. So I am always a fan of what some people call basic science, right? I don't think that science helps people all the time and has for many, many centuries, but I don't think that we should be funding science solely on whether a new drug can happen, whether a new therapy is right on the edge of happening, whether there's something we can sell, right? And one of the things that gain of function has really shown people like me is that when you set the conditions of what scientists will and won't do through money, you sometimes get these really kind of problem effects, right? Just like any other kind of market economy. So I truly believe that it's not just about the rigor, but it's about understanding all of the most basic elements of biology in a really foundational way that would allow us to turn biology into a much more mature discipline where we can make choices about how we study things in very, very different ways.
And one more question. I'm not gonna keep you long here. With the rise of AI and mechanized like research and processes coming into science, would you consider robotics and AI a possibility to be implemented into gain of function research to lower the possibility of human error, um, potentially poisoning that?
Yeah, I think that so people are talking about this a lot at the moment. I mean, I'm happy to send you, CJ, a list of all because a postdoc of mine and I are actually doing this research right now, looking at the rise of what's called AI X bio. So AI X bio. Um, and people do have this kind of concern that AI might make this kind of research easier. One of the things I would point back to is that the data in biology that we have is, in most respects, not nearly good enough for what's called generative AI to come up with new ideas, right? So, in artificial intelligence, the reason that you can tell AI to write you a story, right, is that there's so many stories on the internet that the AI has been trained on that in a very, very deep way. It's the same reason that AI is actually pretty good at making pictures, right? Even though the pictures look a little goofy sometimes, there's so many images out there that the AI can learn from that it can then process and create new pictures. Um, Biology isn't like that, right? Biology would be like you tried to train Chat GPT, but all you had was like your local library as the training set, right? It might get you some of the way, but it's not going to get you to a sophisticated enough process to actually do the kind of work that you want to do. And that's just because we don't know enough about genes and what they do in different organisms. We don't know enough about how genes interact with each other, how they interact with the environment. Once we know all that, then AI would really kind of be an enabler because the thing that AI is really good at is doing a task many, 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 many millions of times in a second that a human would take a much longer time to do, right? So it can brute force some of these problems again, but it needs the data to be able to do that brute force work. And that's where I think that the AI is not going to be able to do this gain of function research in the short term, at least, because we don't have enough of the background data to really be able to make it happen. And then that says nothing about the fact that so far AI and robots can't do the actual work of putting these viruses together, right? They can print DNA, but they can't actually put it into the cellular machinery that you would need to do to actually make the virus work, right? All you can get is the pieces of RNA that viruses usually are comprised of. And then you have to do it yourself, like a human, with a pipette and, goggles and stuff like that. And so far, the robots just don't have what we do when it comes to that. That'll change. But I think we're a ways off yet because we don't have the basic technologies.
Thank you again, Dr. Nicholas Evans. I appreciate your time. I have so much information to write on, so thank you again.
Yeah, let me know if you have any other questions. Happy to talk.